Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 2, Derivatives. Section 2.7, Tangent Lines, Derivatives, and Velocity.
Lesson 2, the definition of derivative. So let's go ahead. What we just finished saying then is that this expression, f of 2 plus h, is the quantity 2 plus h squared. I'm going to go ahead then and write out what my expression is at this particular a value of 2 and for this particular function f of x equals x squared. So what do we get here? F of 2 plus h, we said, is just the quantity 2 plus h squared. And f of 2, we said, is just equal to 4 for our particular function f of x equals x squared. And that whole thing is supposed to be divided by h. That's part of our formula for the slope of the tangent line. Well, if you notice, what we're left with is really something that only involves h. So we have some complicated expression of h, which we are asked to find the limit of as h approaches 0. This is really just a limit problem like we had in the previous sections. So to find the limit as h goes to 0, well, notice that the numerator is really a polynomial. If you were to square this out, you would get h squared plus 4h plus 4. You have a minus 4. That's some polynomial in the top. H is in the bottom. That's another very simple polynomial. So I have one polynomial divided by another. That's a rational expression. And how do we find the limit of a rational expression? Well, as long as the denominator does not have a limit of 0, remember we said we could use direct substitution. So what would that mean? It would mean to find this limit, I'd go ahead and say, oh, I'm just going to replace h with 0 in the top. And I'm going to replace h with 0 in the bottom. But notice in the top, I get 2 squared, which is 4, minus 4, or 0. And in the bottom, I get the very thing that I don't want. I get a 0 in the denominator. Because I get a 0 in the denominator, it means we can't use direct substitution to find the limit of this rational expression. And because I get 0 over 0, it means that we have one of those unfortunate indeterminate forms of our limit. And you might remember, what do we mean by the limit being indeterminate? It means that in this form we cannot tell what the limit is. The top of this fraction is going to 0, the bottom is going to 0. We don't really know which one's going to 0 faster. It's like a battle between the numerator and the denominator. And in the form that I presently have this written out, I cannot tell what the limit is. So remember, when you have an indeterminate form, what it really means is not that the limit doesn't exist, it may or it may not, but just that we can't tell yet what the limit is, and that we must rewrite our expression to try to figure out what the limit is. So I'm going to sort of cross this out. This was just checking to see that it was an indeterminate form, and I'm going to go from here down to here and say, well, I've got to rewrite my expression if I hope to figure out what the limit is. Well, there are different ways of rewriting this. You could notice at the top is a difference of squares, but probably the most natural thing would be to just FOIL this out. If I FOIL this out, it's 2 plus h times 2 plus h, so I would end up with 3 terms, 4 plus 4h plus h squared. So that's just FOILing this out. And then I subtract off the 4, so I'm bringing that down, and the whole thing is divided by h. Well, notice this does in fact simplify. The 4's drop out. I have a positive 4 and a negative 4. Those add up to 0, so that looks great. And furthermore, you might notice that the terms that are left in the numerator both have a common factor. I have a 4h plus h squared, and those both have a factor of h. So let me go ahead and factor that out. So I'm going to pull an h out of the numerator. I would be left with, let's see, a 4 plus an h. And then this whole thing is still divided by h. Now you could argue that this is another rational function, and as h goes to 0 I could try to figure this out by direct substitution, but you notice there's a factor of h in the top and a factor of h in the bottom, both of which are going to 0. So I'd get back to this indeterminate form if I tried to use direct substitution at this point. However, I could go ahead and say, gee, I have a common factor of h in the top and h in the bottom. I can cancel those, and remember that we are looking at the limit as h gets closer and closer, but never quite equal to 0. So I'm not canceling a 0 over 0. H is always something that's small but non-zero. So what am I left with? I'm left with the limit as h goes to 0 of 4 plus h. And I've kind of divided out the things, the factor in the top and the bottom, that were giving me this indeterminate form of 0 over 0. Now I'm finding the limit of 4 plus h. And what kind of function is that? That is a polynomial. And so that means I get to use direct substitution to figure out that limit. And there should be no problem now because there's no denominator that could go to 0. So I just plug 0 in, I get 4 plus 0, and I get 4 as an answer. And what was this 4 equal to? If you follow all these calculations back up here, it's the slope of the tangent line to my black curve at the point P that corresponds to an x value of 2. So this is the slope of the tangent line that I was looking for. That's the answer to this first part of the question. So what we found here then is that the slope of the tangent line at P, at the point corresponding to an a value of 2, is equal to 4. Well, could that possibly be right? Let's look at this blue tangent line that we drew. What we're saying is that the slope of that blue tangent line should be a slope of 4. In other words, if I start at one point on this line and go to another point on this line, I should have something that has a slope of 4. And that looks roughly right. What you're saying is that if you move 1 unit to the right along this line, you should be moving 4 units up to get to another point on that blue line. And it certainly looks roughly right to me. This is definitely a line with a fairly steep positive slope. Okay, great. So now we've found the slope of the tangent line to the curve at the point P. And let's go ahead and find this other thing we were asked to find, the equation of the tangent line. Well, let's go ahead and think about that. So to find the equation of any line, remember that we need really two things. So the equation of a line, we need the slope of that line, and we need a point on that line. So do we have those two things? We definitely have the slope of the line because we want the slope of the tangent line, and we just found that. The slope of the tangent line was equal to 4. So that's the slope of the line that we want to find the equation of. Do we have a point? Well, yeah, this tangent line is supposed to have the same slope as the curve at P, and it's also supposed to go through the point P. And remember, we already found the coordinates of the point P. When x equals 2, you plug in here, 2 squared gives you 4, so the y coordinate, the corresponding y coordinate would be 4. So we do have a point. The equation of the tangent line should be the line that has slope 4 and goes through the point 2, 4. That's the point P on our graph. Okay, you can use different forms to find the equation of any line, and in particular the tangent line. Remember, you can either use the the slope-intercept form, y equals mx plus b. Some people prefer to use that. In this case, when I'm given a slope and a point, I like to use the point-slope formula for a line. And remember, that's y minus y1 is equal to m times x minus x1, where y1 and x1 are just the coordinates of our given point. So that's the 2 and the 4, and m is just whatever our slope is. That will be the 4 that we got. So let's go ahead and plug in. I'm going to do y minus y1. That's just y minus the y coordinate of my point. So y minus this 4 is equal to the slope, which also happened to be the number 4. So that's this slope right here, times x minus the x coordinate of my point, so x minus 2. Alright, so I get y minus 4 is equal to 4x minus 8, or y, if I put it in slope-intercept form, is equal to 4x. I'm adding 4 to both sides, so that would be 4x minus 4. This should be the answer to the other thing we were asked to find. This is the equation of the tangent line at the point P. In other words, at the point where our x coordinate is equal to 2. Well, does that look like the equation of the blue line that we found here? Let's go ahead and graph this and just be sure that it's at least roughly what we eyeballed as the tangent line. I'm going to graph it in green. If I were to graph this, y equals 4x minus 4, it's a line with y-intercept negative 4. So it crosses the y-axis at negative 4. And it's supposed to have a slope of 4. You could think of it as 4 over 1. So I start at my y-intercept, and I would want a rise of 4, 1, 2, 3, 4. So I go up 4, and I'd want a run of 1. So I go over 1. So it would be the line through this point and this point, and it does look like that would actually end up lying right along the blue line that I originally graphed here. So it looks like this formula did give us the tangent line, the same line that we eyeballed as being roughly the tangent line to the graph y equal x squared at the point P. Okay, great. Let's go ahead and look at this same function. Okay, so let's look at this same function, f of x equals x squared. And now the question is, what if I ask you for the slope of the tangent line to our same parabola, but at a bunch of different x values? So instead of just at x equal 2, I'm going to ask you to find the slope at 1, at 3, at 0, at negative 1, at negative 2, at negative 3. Well, of course, one way to go through this would be to say, great, I'm just going to go through the formula exactly as I did before, and first of all I'll replace a with 1 just as we replaced it with 2 on the previous page. Then I'll go through the whole formula again with a replaced with 3, then 0, then negative 1, then negative 2, then negative 3. You're going to have to do 6 pages of calculations similar to what we did on the last page. Well, that seems like a lot of work, and also if you start to go through it, you'll see that you're doing exactly the same steps, mainly because we are using exactly the same function, f of x equals x squared. Let me write out the formula again for the slope of the tangent line at A, and this is just our general formula that we developed. We said it's the limit as h approaches 0 of f of a plus h minus f of a, that whole thing divided by h. And on the last page we replaced a with 2, and then we figured out what f of 2 plus h minus f of 2 was for this particular function, f of x equal x squared, and we did a whole bunch of steps to eventually find a limit of 4. Well, instead of replacing our a value with 1 and going through the whole calculation, and then replacing our a value with 3 and going through the whole calculation, why don't we just go ahead and find the find the slope of the tangent line at a general value x. And we'll just leave x as an unknown. Later at the end, once we've done all of the steps in our limit calculation, we can always replace x with 1 and then replace it with 3 and so on. So let me show you exactly what I mean. we're going to find the limit as h goes to 0 of, and instead of replacing a with each of these x values that we're asked to find the slope at, we're going to go ahead and just replace the a with a general value x, a general variable x. So I'm going to replace this a that I see here with just some unknown x. And I'll do that in both spots. So I'm going to do f of x plus h minus f of x all divided by h. On the last page, our x value was 2, but now I'm just going to leave x as some unknown. Think of it as some fixed number like 2 or 1 or 3, but we'll just leave it as a variable so that it can be an unknown. Well, of course, we have to figure out what each of these expressions is for our particular function, f of x equals x squared, and that's not too hard to do. I'll do it down here. Let's see, where can I do that? I guess I can do that. Oh, let's try to squeeze it in right here. If I want f of something, we know that that's going to be that something squared. That's for our particular function, which is the parabola f of x equals x squared. So for example, if I want f of x, I notice that's one of the expressions up here in the numerator. Well, I just fill in my empty parentheses with an x. So I'll really just end up with x squared there. If I want this other expression that I notice is up here in the numerator, that's f of x plus h, what it means is I take my empty parentheses, and everywhere I see empty parentheses, I replace them with what's here, x plus h. I want f of x plus h. How do I get that? I slide an x plus h into my set of empty parentheses. And f of x plus h then would be x plus h, that quantity squared. Okay, so let's go ahead and plug in. I'm doing the limit as h approaches 0 of, and f of x plus h, we just got through saying here, for this particular function, becomes x plus h, that quantity squared. And the other thing that I see in the numerator that I'm going to be subtracting off is f of x. Well, for this function, of course, f of x just ends up being x squared. So f of x is just x squared. And according to my formula, I divide the whole thing by an h. All right, that looks pretty good. So now we have a limit as h goes to 0 of this thing, x plus h quantity squared minus x squared all divided by h. Remember, we're thinking of x as being some specific value, like 1 or 3. So think of x as being some constant. It's unknown, but it's a constant. The only thing that's really going to be changing in this expression as we do the limit is h. X is staying fixed, and h is the thing that is approaching 0. If you were to try to do this just by direct substitution, you notice that you would end up with an x plus 0, would be substituting 0 in for h. So you get x plus 0 squared. That would just be x squared. And when I subtract x squared, the top of this would be going to 0. Let me put a little arrow here. And in the bottom, of course, as h approaches 0, the bottom is h, so that's going to be approaching 0. And you notice that I get my indeterminate form just as I did on the last page when my x had the specific value of 2 written down. So we can't do this by direct substitution, and in fact, we end up getting an indeterminate form. All that means is that we need to rewrite. And we're going to rewrite using exactly the same steps that we did on the previous page when we had a specific value of 2 in place of the x that appears here. So how do I rewrite? Well, I'm just going to square this out. I'm going to multiply quantity x plus h times quantity x plus h. I will get an x squared. My middle term will be xh plus xh, which is the 2xh, and then I'll get an h squared. So that's just multiplying out that expression. I still have a minus x squared in the numerator, and I'm just going to pull that down. And the whole thing is going to be divided by an h. Notice that some things simplify, just like they did in our calculations on the last page. I have a positive x squared and I have a negative x squared. Those drop out and add up to 0. So I end up with the limit as h goes to 0 of 2xh plus h squared, all divided by h. Now if you just plug 0 in for h again, you'll still get 0 in the top and a 0 in the bottom. So you still get this indeterminate form of 0 over 0. Can you see another way of simplifying this further? If you look at what we did on the previous page, we noticed that there was a common factor in the top. And what is the common factor in the top? Well, both of these have a factor of h. Let me pull that out. I would be left with a 2x plus an h inside the parentheses. And now what can I cancel? Now I can cancel the common factor of h in the top and the bottom. So I am left with the limit as h approaches 0 of 2x plus h. Remember that we're thinking of x as a specific number, so think of x as a constant. The only thing that's approaching 0 is the h. We sometimes say that this expression is a polynomial in h if we think in our minds of x as being a constant. So the only thing that's going to go to 0 is this h here. So I will end up with 2x plus, and the h will get closer and closer to 0. Its limit will be equal to 0. We're really using direct substitution in here. And I end up with 2x. Well, what is all of this saying? The slope of the tangent line at any particular x value for this particular example, f of x equal x squared, turns out to be 2x. So I'm just going to write down here, remark, we get a formula for the slope of the tangent line at x. We get the formula that at any particular x value, the slope of the tangent line will be 2 times whatever that x value is. So the slope of the tangent line turns out to be given by this little formula, 2 times x. Well, what does that mean? We were asked to find the slope of the tangent line at these various x values. Let's go ahead and write down. I've got when x equals 1, now I have a little formula for the slope of the tangent line. The slope of the tangent line is supposed to be 2 times whatever my x value is. So if x is 1, slope of the tangent line will be 2 times 1. I'm replacing this x with a 1, and I get a slope of 2. On our graph, what that means is that if I look at the point on my black parabola corresponding to an x value of 1, well, what point would that be? That would be this point right here. That's the point on the graph corresponding to x equal 1. The slope of the tangent line at that point is supposed to be a slope of 2. Well, if I drew the tangent line in here, I don't know exactly what it looks like, but maybe something like this. The slope of this blue tangent line at the point corresponding to x equal 1 is supposed to be 2. Does it look like that could be right? What we're saying is that if we move 1 unit to the right on this blue line, we should be moving 2 units up, and it looks like that could be approximately right over 1 and up 2, at least within the bounds of the inaccuracy of drawing this parabola by hand and drawing the tangent line by hand. Well, we were asked to find the slope of the tangent line at a bunch of other points, x equals 3. Let's see if we can do that. When x equals 3, the slope of the tangent line, I'm just going to use this formula. It's 2 times whatever my x value is, and now my x value is 3. The slope of the tangent line to this curve at the point corresponding to an x-coordinate of 3 is supposed to be 6. Well, could that possibly be right? Well, here's 3 on my graph, and I believe this is the point. My graph isn't too accurate, but I believe this is the point corresponding to x equals 3. If you plug in, you'll see it's the point 3, 9. and the slope of the tangent line at that point is supposed to be 6. And I can see that it is going to be a very steep line with a positive slope. So I want the tangent line, the line that runs right along the curve at this point, corresponding to an x-coordinate of 3. And it does look like a steep positive slope. This is supposed to be a slope of 6 or 6 over 1. So this line, if I move over 1 unit, I'm supposed to be moving up 6 units. And that looks like it could roughly be right. So the slope here was a slope of 2. My y scale is a little bit crunched compared to my x scale. And the slope of this tangent line was supposed to be a slope of 6. And that looks like it could be roughly right. Remember, on the previous page, we found the slope of the tangent line at the point corresponding to x equal 2, the point 2, 4, and we found that the slope of that line was 4. Does this make sense to you? Are these tangent lines getting steeper and steeper? They ought to be, because the slopes that we found are getting bigger and bigger. We have a slope of 2, then a slope of 4, and then a slope of 6. And it does look like my tangent lines are getting to be steeper and steeper. In other words, they have larger and larger slopes. So that looks like it all matches with our calculations down here. Okay, let's go ahead and see if we can find a couple more of these things we were asked to find. X equals 0. The slope of the tangent line is supposed to be 2 times whatever my x value is, so 2 times 0, and that gives me a slope of 0. What does a line that has slope 0 look like? Remember, a line that has slope 0 means that you're going over some amount. You could think of it as 0 over 1. So your run is some amount such as 1, and your rise is 0. So you go over, but you don't go up or down at all. So let's see if that looks like it could possibly be right on our graph. We're going to find the point corresponding to x equals 0. Well, when I plug 0 into y equal x squared, let me write out y equal x squared here, I get an output of 0 squared, or 0. So we're talking about this point. It's right at the vertex of the parabola. And if I drew the tangent line right there, the line that follows this curve the most closely, since it's right at the vertex here, it looks like that line would actually be a horizontal line. I'm going to draw it kind of thick so that you can see it, since it's in blue and my axis is in blue. So it's the tangent line to the curve at the point 0, 0, right at the vertex of the parabola. And it does look like it would be a horizontal line, and what we're saying then is that the slope of that line is 0. That's what our calculations told us, and that looks right from the graph. The tangent line looks as if it would be horizontal, and a horizontal line has slope 0. Okay, let's go ahead and do the other values that we had here. We were asked to find the slope of the tangent line when x equals -1, when x equals -2, and when x equals -3. So let's do that. Slope of the tangent line when x is -1, we do 2 times our x value, so it's 2 times -1, and I get -2 for a slope. Notice that would be the fraction -2 over 1. So we're talking about a line that's supposed to have a rise of -2, which is really a fall, and a run of 1. Well, let's draw the tangent line at the point corresponding to x equal -1. Let's locate that point. Here's x equal -1. Here's the point on our graph corresponding to x equal -1. And the tangent line looks like would be something like this. And what our formula is telling us is that the slope of that line turns out to be -2, or -2 over 1. Does that look right? Well, the line is falling as I move to the right in the positive x direction. So I can see that if I go from one point to another point on this blue line, it does look approximately right. What we're saying is that we have a run of 1 and a rise of -2. I go over 1 and down 2. Or if you like, you can do the rise first and go down 2 and over 1. But that does look approximately right on our graph. Okay, let's do the last two a little bit more quickly. Slope of the tangent line at x equal -2. Well, I use my formula and do 2 times -2. that gives me a slope of -4. So all that's saying is that at the point corresponding to -2 on our graph, that's this point, the tangent line should have a slope of -4. Looks roughly right. I could go over 1 unit. I would have to drop 4 units. So it would be over 1 and down 4, or a rise of -4. And that looks approximately right on my graph. Let's look at the last one. Slope of the tangent line at x equal -3 would be 2 times my x value is now -3, and I get a slope of -6. And if we look at what point that's corresponding to, this is the point corresponding to x equal -3 on my parabola. I draw the tangent line, and that's a steep line, but with a negative slope. It's falling as I move to the right. So we're saying if I go over 1 on this line, I should be falling 6 units, and that looks approximately right. So without redoing this calculation over and over again, I have been able to find the slope of the tangent line to f of x equals x squared at a bunch of different x values very easily, simply by not putting in the specific x values into the formula each time in place of a, but making a just some unknown variable that we called x. It ended up, you notice, giving me a formula for the tangent line. Of course, that only works for this particular function, f of x equal x squared, but if I'm given the function f of x equal x squared, the formula for its tangent line at any x value is going to be 2 times that x value. Well, we get a formula, and notice that it's a formula in terms of x. And of course, another way of describing something that's a formula in terms of x is that it is a function of x. So our formula for the slope of the tangent line at any x value on this black parabola turns out to be some function of x. Every time I give you an x value, you plug it into this formula and you tell me what the slope of the tangent line is to the point on the curve corresponding to that particular x value. Because this is a very important function of x, it's the slope of the tangent line at x, and because we will use this little formula so often, we give it a special name and a special notation. So here's my original function, f of x equals x squared, and the slope of the tangent line at x, we use a special notation for it. We'll put special notation that someone just went along and made up because this function turns out to be so important. And we write an f, that's to remind us that we got this formula from some specific function. We got it from f of x equal x squared in this case. And then we put a little prime mark here. It looks sort of like a 1 at a slight, like a 1 in an exponent, but at a slight slant. And the way that we say this symbol in words is f prime of x. So f prime of x is equal to 2x. And that would be for this particular function, f of x equal x squared. And notice that f prime of x was somehow derived from this original function, f of x equals x squared. It was derived using this long limit formula for the slope of the tangent line at an unknown value x. So since f prime of x was derived from some original function, in this case the original function was f of x equal x squared, we call f prime of x the derivative, because it was derived from f of x, we call it the derivative of the function f of x equal x squared. So a new piece of notation and a new piece of vocabulary, the derivative of f of x equal x squared is simply the slope of the tangent line at x. In this case, it turned out to be the formula 2x. And the notation for that we say in words as f prime of x. It's just the same letter for the function we were looking at, f in this case, with a little prime mark there. And then the of x is just part of the function notation. So we have a new function, namely f prime, which is referred to as the derivative of the original function f. Okay, let's go ahead and look at the next page. What I would like us to do now on the next page is to summarize what we just talked about down here, but in a general setting, not just for the function f of x equal x squared, but for a general function. So let's go ahead and do that, and then we'll do another example with a new function, just so that you can get more used to this idea of the slope of the tangent line at x and also the derivative of a function. So just generalizing what we said on the last page about the specific function f of x equal x squared, we're now going to look at a general function given by the equation y equal f of x, and I should really underline this because we underline the thing that we are defining. The derivative of a function y equal f of x is denoted this way, exactly as we said on the last page, f prime of x, and it's given by, well, f prime of x is really just a special name for the slope of the tangent line to our function f at a general x value. So f prime of x is just the name or the notation we use for the slope of the tangent line at x. And what is the slope of the tangent line at x? That's given by that limit formula that we've been using. It's the limit as h goes to 0, and instead of f of a plus h minus f of a divided by h, remember that if we're doing the slope of the tangent line and we're replacing our a with an x, some unknown value x, it becomes f of x plus h minus f of x, the whole thing divided by h. So this is the formula that we use to figure out the slope of the tangent line at x, and that is what we are now calling, whatever that limit is what we are calling f prime of x. And that's the notation that we use, and the word we use to describe it, it is the derivative of the original function f. So we start with some original function f, we figure out this limit, we get a formula in terms of x, so we get a new function of x, and that new function is called the derivative of the original function, and it is also called f prime of x. Now notice in parentheses here, I also said provided this limit exists. And depending on the function and depending on the value of x, this limit, like any limit, may exist or it may not exist. If it does exist, then we say that's the derivative of our function at x. Okay, let's go ahead and look at a brand new function and just get used to finding the derivative of that function. It will be similar to the calculations that we did for f of x equal x squared, but now we're looking at the function f of x equals the square root of x. And you might remember that the graph of the square root of x looks something like this. It's actually the upper half, since we're taking the positive square root of x, it's the upper half of a parabola that would open to the right and would have an axis of symmetry right along the x-axis. And since y is equal to the positive square root of x, we're only getting the points whose y coordinates are positive, in other words, above the x-axis. And that's why we only get the upper half of that parabola. We are asked to find the derivative of this function, square root of x. And so remember, that's really the same as finding the slope of the tangent line at a general value x. And we just plug into this formula. It looks exactly like our formula for the slope of the tangent line at a, the only difference being that instead of an a, we have an x in place of the a that we had way back in our original formula. So let me write that out. We are finding the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So that's just the formula that we have right here for f prime of x. Same thing as the slope of the tangent line at x. What I would like you to do is to pause the video and give this a try. Try to go ahead and decide, well, what is f of x plus h for this specific function? F of x equals square root of x, and what is f of x for this specific function? That's a little bit easier for the function f of x equals square root of x. And remember that you can use that empty parentheses trick to figure this out. The empty parentheses trick says just rewrite f of x with empty parentheses wherever you see an x. So f of whatever I plug in for this particular function is the square root of whatever I plug in. It's equal to the square root of whatever I plug in. And that will help you to find f of x plus h. So go ahead and try to rewrite this expression where you're rewriting what f of x plus h is minus whatever f of x is for the function f of x equal root x. Then we'll go ahead and do it together when you restart the video. Okay, well, let's go ahead and do at least that step. I'm doing the limit as h approaches 0, and you can see that for this particular function, f of whatever I throw in is the square root of whatever I throw in. So if what I want to throw in is x plus h, that means that's what's going into the empty parentheses here. I'm trying to find f of x plus h, and so that's what has to go into the empty parentheses here. So I get square root of the quantity x plus h. Those parentheses are really unnecessary in this case. You could just write it as square root of x plus h. So this thing that I asked you to find here is the square root of x plus h. We are supposed to subtract off f of x. Well, what is f of x? You could either go back to the empty parentheses and put x in there, or you can just remember that is the function that we were originally given. F of x is square root of x. So this thing is just square root of x. And then according to my formula, I'm supposed to divide that whole thing by h. Now notice that if you were to try to find the limit of this expression, you said, well, what's happening to the numerator and what's happening to the denominator as h goes to 0? You would remember x is staying fixed. Think of it as a constant. H is the only thing that's approaching 0. So if we substituted h equals 0 in here, we'd get square root of x plus 0 minus square root of x. And what is that equal to? That'd be square root of x minus square root of x would be 0. And we're dividing the whole thing by h. H is approaching 0, so if I replace h with 0 in the denominator, I get a 0 in the denominator. And you notice the fact that I get a 0 in the denominator means this cannot be done by direct substitution. And the fact that I get a 0 over 0 means that it is an indeterminate form, just like the last example that we did with the function f of x equal x squared. So unfortunately, we cannot tell yet what this limit is. We have to somehow rewrite. And this particular example is a little bit trickier than the one that we did before. Somehow we have to try to get this x plus h and this x out from underneath the square root symbol. And I want you to try to think about different tricks that you've learned to get rid of a radical expression like this. Essentially what we want to do is to try to rationalize the numerator. So take a moment, pause the video, see if you can figure out how to get rid of these square roots in the numerator. And if you can, go ahead and start simplifying until you get to a point where you do not have a 0 over 0 indeterminate form, but where you can determine what the limit is, where you can tell what the limit is by allowing h to go to 0. So take a moment, pause the tape, give it a try, and if you get stuck, just start the tape again and we'll go through it together. Okay, well, let's try this together, and if you get stuck, it is kind of a tricky one. So we're trying to figure out a way to get this x plus h and this x out from underneath the square root, and I said that you want to try to rationalize the numerator. Well, remember we have a way of rationalizing a numerator. Usually in algebra we rationalize the denominator, but here we're going to do the opposite, and we're going to rationalize the top, the numerator. And to rationalize a difference of two square roots like this, the trick is to multiply by the conjugate. Well, what's the conjugate? It's the exact same expression, except that instead of a minus sign in between, we put the opposite sign in between. I'm going to make that a plus sign. Well, am I allowed to do that? Can I just multiply the top of my expression by something and expect it to be equal to the expression in the previous line? Unfortunately, I can't. If I multiply the top of a fraction by something, I have to multiply the bottom by the same thing in order to keep the expression equivalent to what I had in the previous line up here. So I can multiply the top by the conjugate as long as I also multiply the bottom by the conjugate. I realize that does introduce some square roots into the denominator, but we'll see that that's okay and that it doesn't matter, mainly because we have a plus sign between these square roots instead of a minus sign. Well, let's continue by trying to figure out what that expression simplifies to. So now we're just doing kind of a bunch of algebra, and remember, in order to multiply this out, I have to FOIL it. I'm doing square root of x plus h times square root of x plus h. That's the product of the first. I'm just FOILing out. So square root of something times square root of something is that thing. So when I multiply those two together, I just get what's under the square root, namely x plus h. Then I'm going to multiply the outer terms together. Well, that's sort of a big mess. That's going to be square root of x plus h times square root of x. Then I multiply the inner terms together. What's that going to be equal to? Well, that's going to be equal to a negative times a positive, so a negative root x times root x plus h. And then the last thing I do is to multiply the last together. That's a negative root x times a positive root x. So let's see, root x times root x is just x. So I get a minus x. And the whole thing is divided by this big mess, h times the square root of x plus h plus the square root of x. Well, that might look awful. It does look awful, but can we simplify it? And yeah, actually, we can simplify quite a lot. If you look at the numerator, I have a positive x and a negative x. Those add up to 0, so those drop out. And I have a positive root x plus h times root x, and a negative, if you just interchange the order of those factors, root x plus h times root x. These also add up to 0. That's why we multiplied by the conjugate, so that the middle terms that involve square roots would drop out, and we would rationalize the numerator. Great, okay, so what am I left with? I have the limit as h goes to 0 of, and the only thing that's left in the top is h. And down in the bottom I have h times the square root of x plus h plus root x. What else can I simplify? Well, it looks like I could also simplify the h's. I have an h in the top and the bottom, so I can cancel. Those become just a 1. So I have a 1 in the top over all this other stuff in the bottom. Well, I've canceled out exactly the factor that was going to 0 over 0. So now I should be allowed to let h go all the way to 0 and use direct substitution. Technically, you should use the theorem that says the limit of f over g is the limit of the top over the limit of the bottom. And then you should split up the bottom is the limit of a sum, which is the sum of the individual limits. And we would be using the root limit law that says the limit of a square root of something is the same as the square root of the limit. I won't go through all of those details. Eventually we get to the point where we're just allowing h to approach 0. Remember, x is unaffected by h approaching 0. X we're thinking of as some specific value. Think of x as a constant for this limiting process. And so we would end up with Well, we have 1 in the top. The limit of a constant is just that constant. In the bottom, I get square root of x is staying constant, but h is approaching 0. So I'm going to replace h with 0. And then I have plus the square root of x. Remember, that is unaffected by h approaching 0. That's the only thing that's going to 0. So I end up with 1 over, well, root x plus 0 would just be root x. And then I have another plus root x. So it looks like I get 1 over 2 times square root of x as my answer. Okay, and so we get 1 over 2 root x. And what have we found? Well, if we go all the way back up here, notice we were finding f prime of x. So this 1 over 2 root x is f prime of x, the derivative of the function f of x equals root x. So what we found here, this 1 over 2 root x is f prime of x, the derivative of f of x, where f of x is the function square root of x. Okay, well, we've applied the definition. What does that do for us? We've found f prime of x. In other words, we've found the derivative of our function root x. And don't forget that f prime of x is really another way of saying the slope of the tangent line at some x value, whatever x value you want to find it at. So the expression that we got here, 1 over 2 root x, tells us a formula for how to find the slope of the tangent line to this square root function at any given value of x. Okay, great. So let's go ahead and use our answer to part A, this formula for the derivative, to find, we're asked to find the slope of the tangent line to this curve, y equal root x, at the point corresponding to x equal 9. Well, we just got through saying that the slope of the tangent line at any x for this curve is the same as its derivative, which is 1 over 2 root x. So if I want the slope of the tangent line at the point corresponding to x equals 9, all I have to do is replace all of my x's with a 9. The slope of the tangent line at 9 is going to be f prime at 9. It's the derivative of our function evaluated at x equal 9. And that just means I plug a 9 in place of x in our formula. So I would have 1 over 2 times the square root of 9. Well, what's that equal to? It's 1 over 2 times square root of 9 is 3. So it's 1/6. That should be the slope of our tangent line at the point on our curve that corresponds to x equal 9. Well, they didn't ask us to, but let's just check that this answer seems roughly correct by going ahead and drawing the tangent line at the point corresponding to x equal 9 and making sure that it looks like, at least roughly, it's a line with a slope of 1/6. So let's see, if I go up here to my curve y equal root x, I'm looking at the point corresponding to x equals 9. So I go up to my black graph. That's the point that I'm looking at. You can think of that as the point P if you want to. And we can even find the y coordinate at that point. We just plug into our function. We're plugging 9 in for x, so the y coordinate would be square root of 9, or 3. And you can see also on the graph that the output value of this input of 9 is equal to 3. And we are talking about the tangent line to this black curve at this point, 9, 3, at the point P. And it looks to me as if the tangent line would have a positive slope. It's going up as I move to the right in the positive x direction, but it's a fairly shallow slope. It's not a really steep line. It might look something like this if I were to extend it. And that looks roughly like the tangent line, or what we would think of intuitively as the tangent line to this curve at that point. Well, the question is, does this blue line have a slope of 1/6? It's supposed to, according to our calculations. Well, remember again that this is the rise would be 1 and the run would be 6. So if I pick any 2 points on this blue line, if I go up 1, that would be a rise of 1 unit, and over 6 units, I should get to another point on my blue line, and that looks roughly right. This does look like a line that has a slope of 1/6, because when I go up 1, I go over roughly 6 units. So this method of finding the slope of the tangent line does appear to work for this specific